So hi to everyone. MEM School of Engineering, Department of PCE, online classes, subject linear integrated circuit. Unit number 4, chapter number 6. So last class we discussed with the single slope and dual slope ADC and its types. So now we are going to see about the A to D using voltage to time conversion and oversampling ADC. Okay, so that is called the sigma delta converters. So where voltage to time conversion. So here the cycles of variable frequency source are counted for a fixed period. It is possible to make an A to D converter by counting the cycles of fixed frequency source for a variable period. So for this, the analog voltage required to be converted to a proportional time period. As shown in the diagram, a negative reference voltage minus VR is applied to an integrator whose output is connected to the inverting input of the comparator. The output of the comparator is at 1 as long as the output of the integrator Vout is less than VA. At T is equal to T, VC goes low and the switch S remains open. When V enable goes high, the switch S is closed. So thereby discharging the capacitor. Also, the NAND gate is disabled. The waveform are shown here. So this is the model of voltage to time conversion. So here also we are using the integrator for defining the triangular waveform and we'll count the data in the output using the n-bit binary counter. Okay, so the reference value on analog input will be compared with the comparator. Okay, first define the voltage at the output. Then whenever the capacitor is charged, it will be charged. When enabled, then only the system will be reset to the condition. Okay. So next one is oversampling ADC or sigma delta converters. It consists of two main parts. One is modulator, another one is digital filter. The modulator includes an integrator and a comparator with a feedback loop that contains a 1-bit DAC. The modulator oversamples the input signal, converting it to a serial bit stream with a frequency much higher than the required sample rate. So this is then transformed by the output filter to a square of parallel digital wave at the sampling rate. The characteristics of delta sigma converts high resolution and high accuracy. So application of this will be no noise and no cost. Typical application of speech and audio. The sigma delta ADC, also known as delta sigma ADC, oversample the desired signal by a large factor and filters the desired signal band. Generally, a smaller number of bits that required are converted using a flash ADC after the filter. The resulting signal, along with the error generated by the discrete level of the flash, is fed back and subtracted from the input to the filter. This negative feedback has the effect of noise shaping the error due to the flash so that it does not appear in the desired signal frequency. The digital filter follows the ADC, which reduces the sampling rate, filters of unwanted noise signal, and increase the resolution of the output. This is the Six Sigma delta oversampling convert. It is having comparator, control logic, controller, and comparator with the voltage reference with the inverting amplifier. So this is the DSC IC, that is DSC 0808, that is a DSC monolithic IC which is having 8 input and 3 outputs. So A0 to A7 are input and V reference in the both the terminal, that is V reference minus and V reference plus and VE and the input output. So DTA converter IC is used for converting 8-bit digital data input to the analog signal output. It is monolithic IC featuring a full-scale output current cycling time of 150 nanoseconds, while dissipating only 33 milliwatt with plus or minus 5 volt supplies. The chip accuracy of conversion is good and the power consumption is also low to make it popular. The power supply currents of the DAC0808 are independent of bit ports and exhibits essentially constant device characteristics for the entire supply voltage range. So these are the features of and electrical characteristics of DAC08 and 08. So 8-bit parallel digital data input, fast settling time, relative accuracy, full scale current match. So non-inverting digital inputs are TTL and CMOS compatible. High speed multiplying input slew rate. So power supply voltage range, low power consumption, maximum power dissipation, operating temperature range will be 0 to 75. So that device takes in parallel 8-bit data from microcontroller and microprocessor that converts the data into analog signal at the output. And the analog output from DAC is a current quantity and is needed to be converted into the voltage parameter for using the application ECU. So to convert the current parameter into voltage parameter, we'll use the op-amp circuit as shown in the circuit diagram. This op-amp circuit is called the current to voltage converter. So this application is analog to digital circuits, electrical measurements, audio conversions, and obvious applications. Okay. This is the typical diagram of the DAC08 and 0. Then ADC IC. So ADC main feature is 8-bit successive approximation ADC, 8-channel multiplexer with the trust logic. Conversion time is 100 microsecond. It eliminates the need for exponent zero and full scale adjustment. Easy to interface to all microprocessor. It operates on single 5-volt power supply. Output meet TTL voltage level specifications. So this is the pin diagram of ADC 0808 and 0809. This is the typical interface of ADC with the circuit diagram and processor. So most ADC and DAC, these circuits used in the microprocessor for converting the analog to digital data and digital to analog data. Okay, both the ICs are in the 8-bit conditions. Okay. So up to this, we finished unit number 4. In unit number 4, we discussed in the DAC types and the analog to digital converter types. Okay. Let's see one by one. Okay, next class, thank you. So next class we'll see the unit number 5. So that is special function ICs and waveform generators. So that is the different models, different ICs used in the application of the application. Thank you.